And right now I'm in my office, and before starting to speak about testing quantum mechanics underground, I want to remind Giancarlo Ghirardi. Yesterday, there were 4 years since he unfortunately left. We are here in Trento, in the beautiful surrounding of North Italy, together with Reinhold Bertelmann and with my friend Beatrix Ismayer. And right now I'm in my office, actually in this building here, which you can see in this, Laboratori Nazionale di Frascati. I'm showing you this not because I'm going to talk about, but just to give you some ideas about the background my group has and how we arrived to do experiments. I'm an experimentalist in Gran Sasso. So as you have here, as you see here, we have a building which actually hosts a particle accelerator, very beautiful. It's a collider, electron-positron collider. This is a picture from inside where we do experiments which are measuring X-rays, so radiation, which in our case, that's a picture from above of the collider, which is colliding electrons and positrons and generating strange quarks in forms of K- mesons, for which we form exotic atoms, and we study the properties and decays of those exotic atoms, which contain strangeness. That's part of my group in the accelerator. And to do so, we use radiation detectors. So our group is expert in radiation detectors, and that's how we also got in Gran Sasso. Because while doing these experiments, which have to do with neutron stars and the equation of states of neutron stars and strong interaction, we were wondering what else can we do with our beautiful radiation detectors. And that's the story I'm going to tell you in what comes, how we are kind of sneaking into the God's cards, which is actually the title of a book written by Giancarlo Ghirardi. And the laboratory where we work for this second type of experiments is not so far from us. So Frascati is near Rome, it's 20 kilometers southeast of Rome, while Gran Sasso is below the Gran Sasso mountain, 150 kilometers far away from us. It's really under this mountain, you can see here, where there are many experiments which are doing kind of, sorry, I'm having a cold, exotic physics, looking for dark matter, neutrino physics. And one is doing experiments there because differently from the labs which are on ground, you are sheltered from the cosmic rays. Sorry, excuse me. So you are sheltered from the cosmic rays, and we are not really underground as other experiments are in a gold mine or something like that, but under a mountain. And we are having here a reduction of the cosmic background by 6 orders of magnitude. And when, as in our case, you look for signals which might not even be there, of course, you'd like to do this in the so-called cosmic silence. So without the signals which might fake what you are looking for, but are absolutely easy to understand through the cosmic rays. And the lab, it's, as I told you, it's under the mountain, which is a 1,400 kilometers tall mountain, 4,000 water equivalent, meters water equivalent. And it's situated in a gallery which is connecting 2 towns, L'Aquila and Teramo. And this gallery, it's pretty long, so here are cars circulating, it's 10 kilometers long, and halfway there is an opening which goes straight into the lab, which actually has 3 big holes, like 3 big cathedrals, so it's really impressive. And beyond this, and I hope I could host you one day to do a workshop there, it's really a beautiful surrounding. And beyond that, there are many other boxes hosting smaller experiments. That's the entrance. You see here the gallery where cars are circulating. And this is the entrance in the lab where you go if you are doing experiments there. And it looks quite impressive. Our experiments, it's situated in one of these boxes, so it's not a big experiment. It can be hosted in one of these boxes. And that's what we do, what I'm going to tell you and what comes next. That's a drawing of my electronic engineer. It's somehow two different things which are really quite different. So we are looking for radiation in terms of X-rays and gamma radiation, which is connected with two types of physics. One, it's the collapse models, which Angelo has introduced from theoretical point of view Tuesday, so he was the first speaker. While the other one, I'm not going to talk too much about it, but still I mention it because it's rather interesting. It's possible violation of spin statistics in terms of Pauli exclusion principle violation. And by doing this, we are studying the relation between quantum and gravity from various points of view, which I will try to explain. That's us, part of us in 2020 during pandemic time, where we could still access the lab, but with special, let's say, special measures. This is part of our experiments, which you don't really see because it's embedded into layers of copper and lead, which is still needed because we need to shield the radiation coming from the rocks, like radon coming from underground, and uranium and plutonium, uranium chain decays from the rocks themselves. The first thing which I'm going to talk about, it's collapse models, which again in this community does not need any sort of introduction. It's related to the measurement problem, and of course there are quite a few solutions here. It's not even a complete list. I only list the de Broglie bomb and many world interpretations, for which, in spite of their very attractiveness, it's very hard for an experimentalist to do something, even if quite recently some activity in that context of de Broglie bomb was put forward, but we are still discussing. The collapse of the wave function in the terms of wave function reduction with the collapse models introduced by Angelo, it's very attractive because these models, as he was introducing, are adding new terms into the Schrödinger equation, and as such, it's not an interpretation, but it's a rival theory of quantum mechanics. Actually, would be the first sign that one should look for a theory which is beyond quantum mechanics. And the reason to do that is connected with the search of a physical mechanism which is producing the wave function collapse. And that has been explained by Angelo. And if you're looking for a reason for the wave function collapse, one might also do the ansatz that gravity might be connected, even if this is wrong, that's a wrong statement. It's not necessary that gravity causes the collapse, but gravity might be still related with the collapse. And that's by itself extremely, extremely attractive. I'm also going, since we speak about consciousness, tell you what is the outcome and what's the impact of our findings, recent findings on some of the models, actually on one of the model of consciousness, in particular the Orch OR model of Penrose and Hameroff. And I mentioned here that what you do in these models, you add additional terms to the Schrödinger equation, which would never solve the measurement problem because it's linear. So whatever you have, you propagate to infinite. And in order to cut down the linearity and the superposition, you need to add terms which are not linear anymore, but they should be chosen cleverly, because otherwise you screw up what you already know and you measure from quantum mechanics. And again, who is interested, I refer to Angelo's basis talk for more theoretical ansatz. However, I repeat part of these slides he had, in particular the fact that what you do is add new terms which are nonlinear but should be chosen clever. And of course, this is not a theory but a model. And as such, you have parameters. In particular, you have two types of parameters, depending whether you are speaking about a generic model, like the case of continuous spontaneous localization, where you don't care what causes the collapse. It's some external noise, which it's kind of interacting with your wave function and collapsing it, but you don't identify in something specific. And then you have the two parameters, which is the correlation length, where the wave function is bound to collapse, and the collapse strength, which is a kind of giving you a measure of how fast the collapse goes. And the second model, which I'm going to address, it's those which are related to gravity. And again, I don't use here the terms generated by gravity, because as I will explain, at least in one case, in case of Penrose, there is no dynamics there. So you don't really have a connection such as to be able to say that the gravity is the cause of the collapse. In this case, the situation is rather well identified. The superposition of the wave function, it's also triggering the position of two different space-time geometries. And in this case, this does not stand too much, and it's impacting back, it's bouncing back on the wave function with a parameter which has been introduced in this model, which is this R0 parameter. And in this case, again, the collapse, it's random, so it acts on the effective size of the mass density of the particles in position. Is of course random, otherwise you don't preserve the Born rules. And what has been worked out by theoreticians, in particular Angelo and Loyos Giosi, is that this randomness is showing up as a diffusion in the particle motion. Even if the particle would be totally free, it would still wiggle like a kind of Brownian motion. And this also happens in particles which are bound in atoms. It's a continuous randomness in the diffusion of the particle motion, which if particle is charged, it's having as an impact the emission of a radiation, which is called spontaneous radiation. If you ask me whether how we do this with the conservation of energy, the answer is simply does not conserve energy. That's not a theory, it's a model. So one hopes to regain the conservation of the energy if one only finds the real theory behind this model. So this is an empirical model which has this attractiveness from experimental point of view, that you can start measuring radiation, and eventually you can come up either with an experimental proof that somehow you have found signals of the collapse, or otherwise you can set bounds on the parameters of the two models I mentioned before. That's a kind of schematic view. So charged particles in the modified versions of collapse theories are emitting radiation. And oh my God, what happened? That's a picture with me, with Roger Penrose. I don't know why whom I met yesterday in Rome. So he was in Rome, he got the medal, Wheeler medal, and we were talking quite a lot about the model. In his case, so he's not claiming a dynamics, and since he does not claim for a dynamics, he doesn't have a radiation, of course, but this is on one side a bonus, on the other side a drawback, because one is still looking for a dynamics associated with the model. And yeah, so these are the two, let's say, equations which have been worked out by theoreticians relating the rate of the radiation with the parameters of the models. In one case, the continuous spontaneous localization, there are two parameters bound in this lambda over RC square form, radiation emission, while in the other case, the parameter it's only one. It's, let's say, the wave function, more or less dimension, so you can't have a point because this would diverge. And with this additional comment that in the case of Penrose, since he doesn't have dynamics, in principle, there is no radiation, but there is also no dynamics. We were talking exactly about this. And what we did was to perform an experiment in this very clean, from the point of view of the signals, including radiation, which is not the one you are looking for at the Gran Sasso. And we have put extremely strong bounds on the parameters of these models. And by the way, what we have achieved was to rule out the natural, the so-called parameter-free version of the Penrose model, which we published about 1 year ago in a paper in Nature Physics. And that's the paper, Underground Test of Gravity-Related Wave Function Collapse, which, to our surprise, was the second favorite story in this website, which in 2020 among the 10 favorite stories. And in this paper, what we have done was to perform an experiment with ultra-pure germanium detectors in the very clean laboratory of low radioactivity in Gran Sasso to measure the radiation. Radiation which was supposed to come from where? Well, first of all, from the electrons and protons of the germanium detector itself. So the spontaneous radiation from the material which has been used by us. By the way, you can see here, you can't see here the germanium detectors because they are in these boxes of ultra pure lead surrounding them to protect and to shelter them from radiation coming from the rocks of the mountain, so to reduce further the background. And actually the detector, it's surrounded by complicated additional shielding. That's the germanium ultra pure detector. Then we have layers of ultra pure copper and ultra pure lead just to absorb the radiation, which eventually it's delivered by the uranium chains in the mountain. And we have measured the radiation, which was supposed to come from the electrons and positrons forming mostly the germanium itself. And also, of course, with some efficiencies from the copper and from the lead surrounding the detectors. And after 2 months of measurements, we finished with this spectrum, which is the energy, gives the energy function of the, let's say, the number of counts function of the energy. And we have selected a specific region in our spectrum, going from 1 MeV to something like 1.3 MeV, where we were doing our analysis, which was a Bayesian analysis, where we were bounding the parameters of the models. And actually, we bound the parameters R0 from the Penrose model to this value, 0.5, 10 to minus 10, while the other parameter was bound for 10 to minus 13 for RC 10 to minus 7. And the first one, the R0 parameter in gravity-related collapse models, actually exclude, as I was saying, the simplest version of the gravity-related collapse models, which would have preview, let's say, a value around here, so factor 10 smaller than the one we have bound for. And for this, in this sense, we have excluded this type of model, still repeating that these are the simpler versions, and I will come back to this in a moment. And also in a second paper last year, we have set new limits also on the other parameters of the model, which comes from the collapse, so continuous spontaneous localization. Quite recently, another paper from Majorana demonstrator has set even stronger limits, but they used an energy region which is smaller. It's at the level, it's 2-3 orders of magnitude smaller. And we are worried about cancellation effects coming from emission from the nucleus and from the electrons, which we are presently calculating, but our feeling is that they are very, very strong. So we are having some doubts about the limit put forward. We are working on this. Nevertheless, this proves that this is a very interesting sector, and more experiments by searching for this radiation can do sensible searches of the collapse models in all their forms. Ourselves, we are doing now a new experiment with a different germanium detector. You can see here finally the germanium detector in the box of pure lead which is surrounding it, and that's part of the group last month, where we were doing installation of the new experiment and started the new data taking, which is ongoing and we are soon to be analyzed, also in the framework of an FQXI funded project. And of course, this sets a lot of questions. Now, of course, we do not have yet signals of the collapse. We are binding the parameters to stronger and stronger values, but sooner or later, these questions which are set here, relation with gravity, eventual relation with the dark sector, and with a possible theory beyond quantum mechanics will pop up. We were also discussing this in a workshop kind of 2 years ago, in December, actually 1 year and a half ago in December, where we were exploring the link between this type of issues and discussing the impact of, let's say, the possible future. You might recognize some of the people. David, you can see him here, and Kelvin, I think you were also giving a talk here, and this is Roger Smolin. So yeah, we were chatting about possible, yeah, you are here, Kelvin. And we were discussing all these things, but since then there is some progress. So this was 1 year and a half ago, and it was actually some progress, because if I have to do kind of a conclusion of this, the first thing I told you is we are trying to work out how to go from to be and not to be Schrödinger cat to be or not to be, which is what actually we see in the macroscopic world. This it has received attention and grant from FQXI and from the Templeton projects. From the FQXI, we are actually together with Loes Georgi and Maneli Derakshani, we are working out the impact of our findings, of our future experimental findings, on this orchestrated objective reduction theory of consciousness. And some days ago, which comes very nicely, we published a paper in Physics of Life Reviews, which is called At the Crossroad of the Search for Spontaneous Radiation and Orch OR consciousness theory, where we were kind of musing and investigating the impact of our finding on these models. Now, I'm not an expert of tubulins and neurons, and I won't claim I am. So I won't give any sort of details about the structure of neurons and tubulins. The only thing which matters here for us and why attracted our interest is that this theory, this model has two pillars. One, which there are two very strong claims. One is that there are coherent states in bundles of tubulins inside the brain, which by itself seems to be rather crazy, because as we know, the brain is wet and humid and hot. So one might wonder how one can build this type of coherent superpositions, but that's not what we worked on. What we worked on is that on the top of this, the other pillar of this model is that the consciousness is realized by collapse of the wave function induced by self-gravity of these tubulins, of these bundles of tubulins, with a time scale which is somehow correlated with indicators like waves, alpha, beta, gamma waves in the brain. So it's a frequency which is at the level of some milliseconds, so up to 500 seconds. So it's like quantum coherent states are being created and they collapse. Whenever they collapse, it's a moment of consciousness. And we investigated the second pillar, of course. So what can we eventually say from our finding, actually from the bound we put on these Dioggi-Penrose models in our paper in Nature Physics, on these models. One needs, however, to do a note here, which is quite important, that Penrose, which we also wrote in the paper, has expressed to us that he regards the feature of the spontaneous radiation as unphysical. He doesn't have a dynamics. Even if both models, Dioggi's and Penrose, Dioggi has a dynamics, are ending up with the same time of the collapse, which is the H constant over the self energy between the two superimposed states. So they both end up with the same scale time. The difference is that Dioggi is kind of relating it with gravity, while for Penrose it's more an ansatz without dynamics. Nevertheless, lacking a dynamics, we took the dynamics of Dioggi and worked out the implications starting from spontaneous radiation, which we found previously. So if indeed what we have found, namely the limit on the R0 parameter put in our Nature Physics paper, needs to be taken seriously, what can we say about the Orch OR model and the way in which it's supposed to work in various contexts? The first context, it's the one in which well, there is a problem here that one does not actually know where the superposition of states, or where the quantumness it's entering, whether whether it's entering at the level of separation between possible quantum states, which it's at the level of nucleons, or at the level of proteins, so entire smooth out proteins, or even more at the level of atomic nuclei. And we have worked out actually two solutions, the level of atomic nuclei, taking the carbon nucleus as a reference, and the first one, the entire smooth out protein, where the separation is at these two levels. And what we concluded here is that if we take the first case where the separation is at the level of at the level of 2.5 Fermi, so at the level of atomic nuclei separation in the states inside the two bodies, you end up with the necessity, if you want to have a signal which has a frequency of 25 milliseconds, you end up that you need about 10 to 23 tubulins. And if you work out the number of required neurons for this, you come up with 10 to the 17 neurons, which is definitely far, far too big. And because it would mean that, a big portion of the neurons in the brain should build up the coherent state, which seems to be absolutely far too, let's say, far too incredible. And this seems to be not a very plausible assumption. So then we turn our attention about partial separation of tubulins, taking into account that this might happen at the level of the proteins, in particular the actin. And in this case, again, there are two possible cases. The one in which the separation is much smaller than the dimension level of the protein, and the second in which they are comparable. And what we obtained in the first case, so when the level of the separation delta X is much smaller than the length of the protein, we came up with what I show you here, that we need actually 10 to the 10 neurons. And 10 to the 10 neurons means that about 10% of neurons in the brain should be involved in this process for 25 milliseconds. Time scale, of course, if we relax it a bit, we would need 1% of the brain to be involved. The other case where the separation is at the same level, which is, however, very big, it's about at the level of nanometers. Nevertheless, as the dimension of the protein comes up with a number of neurons to be involved, about 1 million. So while for 500 milliseconds signal, it's about 10 to the 5. And yeah, so of course, this says nothing about how one can build up this type of big, huge systems like 10 to minus 16, minus 17 kilograms from the point of view of coherent state. So we don't make any claim here of how this can actually be built. But however, this seems to be a little bit more reasonable from the point of view of percentage of the brain, which is required. Our conclusion in this paper was nevertheless that in our consideration of this simplest version of the gravity-related wave function collapse in the dynamics taken from the Dioggi version, in this inquiry, what we can conclude from our research of spontaneous radiation is that none of the scenario, with perhaps the possible exception of partial separation of tubulins, what I showed you in the last, seem to be plausible. But however, this does not, in our opinion, rule out Orch OR theory. Actually, this makes it even more interesting. More interesting because that means that real work could be started now. Because I remind you that what we have actually excluded, it's a simpler version of the model where there is no dissipation, neither Markovian effects, non-Markovian effects there, memory effects there, which pushed us now to work together with theoreticians on these new models where we are implementing presently this type of dissipation and non-Markovianity. And of course, this does not say anything about how this type of states might be created, which we are not experts, but there are other groups of experts like the one led by Jack Tuchinski in Canada, who are working on the second pillar of this Orch OR theory, and he has obtained quite interesting results, which I don't comment because it's he who is working on this sector. We're collaborating and we are setting up a cross collaboration on these two pillars. However, these models, so the modified version of with dissipation and non-Markovianity, are also worked out in the framework of a John Templeton project, which is exploring exactly these quantum boundaries in many body systems in gravity-related collapse models. And in next 5-10 minutes, I'm going to tell you something completely different. So this concludes the parts related with collapse models and impact on Orch OR consciousness model. And since I think this is also interesting because it's another aspect of the relation between gravity and quantum physics, is the other search we are doing, search for possible violation of the Pauli exclusion principle, where we are actually looking for possible violation of relation between spin and statistics, which in nature is realized either in the bosonic form or in the fermionic one. But of course, one might also wonder about the mixed symmetry states. And if one does this, one needs to go to the root of spin statistics theorem and see what out of the postulates set there might not be viable. And this has been worked out by Wally Greenberg already years ago, where in a paper he wrote on this, he was proposing the parastatistics models and algebraic violations in forms of Q-on theory. He said that there are many reasons to look for it, like violation of other symmetries, like CPT or Lorentz, or the space-time properties like non-commutative space-time geometries. And what we do is we look for atomic transitions prohibited by the Pauli exclusion principle, namely atomic transition bringing a third electron on the fundamental level. Since I know that there are some philosophers there, I have also to mention a beautiful book written by Michela Massimi related with searches for the Pauli exclusion principle. Because of course you are also investigating in this context the relationship between well, we don't know whether electrons are identical particles or non-distinguishable particles. Sorry. And also from philosophic point of view, this is an interesting search. So we look for this energy, for this prohibited transition. And we do this in the framework of an experiment, which it's looking for atomic transitions in copper, circulating a current, so to integrate a lot of currents which we are interrogating. Are you respecting the Pauli exclusion principle or not? And the experiment is pretty complicated. It has silicon detectors as X-ray detectors, has a complicated vacuum and cryogenic system. And that's us in front of the box. And we have set extremely strong limits on the probability of violation, which go to 10 to minus 42, which is really one of the strongest limits in physics you can think of. And presently, we are expecting to go even beyond that, so to gain other 2 orders of magnitude, also with different type of setups. But what is interesting in this context, what we are working out now in collaboration with 2 theoreticians, it's the relationship between our findings and particular type of non-commutative space-time geometries embedded in quantum gravity models. So there are quantum gravity models, both in string theory and in quantum loop models, which are translating into violations, possible violations of the spin statistic through the non-commutativity of space-time, which is energy dependent. So you have a scale, and this scales with the energy. And this is something which we are presently working on, the limits on the parameters of these quantum gravity models as seen from the violations of the Pauli exclusion principle point of view. And we succeeded to set limits which are extremely strong, much stronger than Large Hadron Collider. Like one, it's beyond the Planck scale. The other one in the theta Poincaré, it's approaching the Planck scale, but still not reaching it, which is absolutely fantastic because it's another way. It proves that there are many clever ways to look for quantum gravity effects, even if you don't push in energy, but you have a very, very refined experiment able to do extreme precision searches and like our own. And also I have to cite Lev Okun, whom we had the pleasure to talk with years ago. Now he died, unfortunately, who was one of the persons who mostly worked in this and in non-conservation of charges, who was really claiming that the search through all the periodic table of possible violation is of special interest. And if you are interested to know more about this, we wrote some years ago an article in CERN Courier, which is for general public. So it's a kind of a history of how it came into being, and also how and where we do searches of possible violations. We are also considering the idea to extend our searches in Australia, actually in Southern Hemisphere, because there are features which you cannot test if you only stay in the same hemisphere, like seasonal variations, systematic effects from seasonal variations, and all sorts of things, also directions in space, if you think that there is some cosmological implication there. And here is the Stawell laboratory near Melbourne, together with Elisabetta Barberio, the head of this lab. We are discussing this differently from ours. It's really an underground mine, ex-gold mine at nearly 2 kilometers depth. So it's a completely different environment, where differently from us, where the temperature is 16 degrees almost constantly. Here it's quite harsh. It's 30 something, 35 degrees. So it's really a different type of environment. So we hope to extend our search also in Southern Hemisphere, like for example in Australia. And with this, I arrived to the end of what I wanted to share with you. Of course, I thank all my financing projects, particularly to FQXI Foundation and to John Templeton Foundation. And of course, I thank to you for having given me this possibility to address to you and tell you what is our type of research in this context. Thank you very much.
Questions? Johannes? Yeah. Can you see me? Yeah. Yeah. Hi there. Thanks for the talk. Very interesting.
Hello.
So, I was just wondering, since you mentioned, non-Markovian models, or maybe just like Markovian models, which look very different from what you have, do you have any estimation of how well the previous results carry over to these?
Oh, definitely the previous results will transform in much weaker results, because in dissipation you have cutoffs, and in non-Markovian models you have effects which might damp your results. So what we expect is that our very strong limit would be translated into much fainter limits. However, this would be the very first search of this type of limits. And I have also to add that there are other methods indirect. Well, of course, one is the interference and the disappearance of interference, which is actually put forward in Vienna, but it still needs to catch up. The other one is optomechanics and heating, which addresses a completely different frequency level, which makes it very interesting, because in that case, that one might be much stronger if you have the dissipation shifting the limits there. So it's very, very interesting to fill the gap and to do this search in all the frequency domain, going from optical and optomechanics up to the X and gamma ray. So it's actually very, very exciting. That's only combining them, you might learn how the elephant is built, because right now all worked on a sphere, touching it, it's always the same. You conclude it's a sphere, but now we look for an elephant. We touch it from different points, and it would be extremely interesting to put together all this knowledge.
Thanks very much.
Same to you.
Questions? Can I ask you about just how you're thinking about the relationship between models versus theories, particularly as it pertains to the energy conservation issue? So if I understood, you were saying that you think some of these parameters like lambda and these predictions, such as the violation of energy conservation, won't really be a part of the ultimate collapse theory. They're just sort of incidental to the current model that we have.
Yes, I discussed this, so I have to report what I have discussed on this with Steve Adler, because I addressed to him, he's one of the persons involved. He told me the following, that we shouldn't be worried, because when we will have a theory, we will regain the energy conservation. Okay, this I could have figured out by myself, but where you can regain it? Well, there are tentatives today, even some articles written that dark energy might be somehow the counterpart of the spontaneous radiation. And as far as I know, there are already some publications which are trying to connect the dark energy sector with the spontaneous radiation. I don't know how much successful they are, but it's let's say a way to go, because in this way you might figure out what could be the counterpart of spontaneous radiation. Steve Adler has its own model, which is beyond the trace dynamics, which goes beyond the present quantum mechanics, which in his view might be, let's say, a new theory which arrives to quantum mechanics as an approximation. So these are examples which might be neither complete nor correct, but at least it's how things could be figured out, and one could go to sleep in peace that didn't destroy the energy conservation.
Okay, I guess I had two puzzles about that, and you just answered one of them. The first puzzle, which you just answered, was like, I don't see how you can remove the violation of energy conservation if you have wave function collapse. But if you add something in addition to the wave function, such as dark energy, then I can kind of see how that works. So I see. But then I guess the second point is, why do you feel the need to recover energy conservation? I mean, some people think, like Sean Carroll, for example, has been arguing that energy conservation is violated in general relativity. Do you think it really matters if ultimately the collapse theory just inevitably violates energy conservation?
Personally, I don't have a standing there. So I can understand Sean Carroll's point of view. I can even agree with him. But given the standing of energy conservation in all what we have done up to now, before giving it up, maybe one would try to check whether there are ways to preserve it. And it would be extremely interesting to have something which does not really and genuinely conserve energy. I think it would be extremely interesting. But however, I had to add here that these are models. And as models, you don't know what they really hide, because in a theory, you shouldn't have three parameters. You should explain them unless they are embedded somehow from the very beginning in the theory, which is not yet the case. So it's still something to be understood and discovered. And I think this is very exciting, at least for me. It's a very exciting period we are living in this context. And I'm very keen to see what will be next, not only in my experiment, but also in many others with whom we are competing, but in a friendly way.